Hi, I'm Show, like Showtime, TV show, Shogun, for show, show me the money, whatever you guys want. But let me ask though, have you guys ever studied or carefully analyzed the motion of a really drunk man? He takes a few steps to the left, and then back towards the right, and then stumbles backwards before ultimately collapsing on the side of the street. Now that I think about it, some of you may have studied such a motion because you might have been this person yourself. This drunken trajectory is a prime example of a random walk performed by an active matter system. As drunk as we are, we have the ability to self-propel, to move in a directed fashion, and if we wish, to reorient and move off in a different direction. The forces that govern this poor man's motion are primarily gravity and his own inertia. But suppose we shrink this poor, unfortunate soul down to a size of a single tiny bacterium, a few microns in size, suspended in solution. Now, from his vantage point, everything appears bigger, including individual solvent molecules that surround him, that incessantly bombard him from every direction, causing his motion to fluctuate randomly in a process called Brownian motion. Luckily, he has whip-like appendages attached to his body, called flagella, that allow him to again self-propel and to reorient. This drunken trajectory is not of some drunken man, but of a bacterium swimming in solution. Even though the scales of their sizes differ by 6 orders of magnitude, their ubiquitous ability to self-propel, to move, is the key quality that allows this poor man to get home relatively quickly and this bacterium to find food efficiently. Active matter systems are all around us. From birds in the sky to fish in the ocean, these systems have a unique ability to convert chemical energy into mechanical motion. By virtue of their self-motion, these systems have the ability to associate together and to move collectively as a herd. The same is true inside of our cells at the nanoscopic and microscopic world. One example is pathogenic bacteria that infect our cells. Certain species multiply to a point where it causes the host cell to rupture and burst open, followed by a release of bacteria and a spread of further infections within the body. The physical mechanism that mediates the release of intracellular bacteria from their host cell is poorly understood. If we had a simple quantitative method to compute the forces and the pressures that these bacteria exert on their host cell, we may have a better understanding of how disease spreads within the body. Another example of active matter systems at very small scales is motor proteins that shuttle macromolecules within the cell. Just like birds and fish, motor proteins move collectively, and they do so along microtubule highways that are set up inside the cell. They are able to deliver a particular cargo inside of these vesicles to a particular place within the cell. And it makes you wonder, what if there was a way to engineer a particular material or a method to deliver a drug to a particular place within the cell? Such a material or method could change the way we treat certain diseases inside the body. Whether it's developing a theory to predict the bursting of infected cells, or to the development of new materials for drug delivery, an important consideration is the fluid mechanics and the physics of the motion of active matter systems. But before we can understand the collective motion of active constituents inside a real living cell, we need to first understand their general behavior and the motion of a self-propelled body as an individual. And to do that, we're all going to take a trip today. We're going to take a trip to the happiest place on earth. There is a ride at Disneyland where guests hop onto a vehicle about this big. When the ride begins, air vents on the floor of the arena shoot air up, levitating you and the vehicle a few inches into the air. So imagine that you're sitting on a puck of a gigantic air hockey table. But you can lean onto one side of the craft, which gives you a tilt. And since there's air blowing from the bottom, it gives you a self-propulsion in the direction you are leaning in. So let's take a look at this ride. If you track the trajectory of any of these vehicles, it may look something like that. A drunken trajectory. And here's me on that ride looking like the happiest boy on earth, leaning onto one side of the craft, which gives me a speed u0 in that direction. I can also change my mind and move off in a different direction, characterized by a reorientation timescale, tau r. After long times, my motion is going to look like a random walk. A drunken trajectory. And after long times, there is going to be a diffusivity, which characterizes how quickly I spread out or diffuse in space. And that diffusivity d scales as the run length squared divided by the reorientation time scale. In this case, the run length L is simply the speed that I translate times the reorientation time. Substituting that run length into there, we find that the diffusivity scales as the speed that I translate squared times the reorientation time. A more detailed, rigorous analysis of this same calculation gives a factor of 1/6 out in the front, but the important thing is that the diffusivity scales in this way. And at this stage, I'm going to take off this hat because I'm actually quite serious about this result, in that real systems diffuse in this way. One example is living bacteria that undergo a run-and-tumble motion. Another example comes from recent developments in colloidal chemistry that have led to the development of synthetic, non-living active particles that are capable of self-motion. So let's focus on that particle circled in black. It initially propels to the right, and then rotational Brownian motion causes it to reorient upwards, and then again towards the lower left. I'm going to show the trajectory of more of these particles, and it looks like that. Again, if you put all of these arrows together, it looks like a drunken trajectory. So let's focus on these particles for a little bit. These particles are typically micron-sized plastic beads where a part of its surface is coated with a catalytic material such as platinum. And these half-coated particles are called Janus particles. In ancient Roman mythology, Janus is a god of transitions, times, beginnings, and doorways. He's depicted having two faces, one looking into the past and the other one into the future. And it just so happens that this Janus god is made out of polystyrene and half of it's coated with a layer of platinum. When we put this particle inside a solution of hydrogen peroxide, the peroxide decomposes into water and oxygen only on the catalytic platinum surface. This creates an asymmetric distribution of reactants and products around the surface of the particle, and species such as dissolved oxygen will diffuse down its concentration gradient, which actually pushes the entire particle in this direction. So let's take a look at an experimental realization of such a process. These active Janus particles have a swimming speed of 15 to 20 microns per second with a reorientation time of about 5 seconds. Now, I'm a theorist, and even someone like me can make these particles, so it's a relatively easy process to do. Active matter systems are often found in confined spaces. So I took these particles, and with some collaborators at ETH, we fabricated an acoustic tweezer device, which employs sound waves to manipulate objects and to confine them to a specific region in space. Suppose that I have a Janus particle with hydrogen peroxide undergoing active motion. When I turn on the acoustic tweezer, the device sends out acoustic rays that interact with the Janus particle. Multiple scattering events occur that transfer momentum from those rays to the particle, which then the particle feels a trapping force that directs it towards the center of the trap, shown by that red dot in the center. An experimental realization is shown right here. All these bright spots you see on the screen are the active Janus particles. Initially, the acoustic tweezer is turned on. So what you're going to see is all of these particles get collected towards the center of your screen because the tweezer is turned on. What I'm going to do next is to suddenly turn off the tweezer so that the trapping force is 0. What do you think would happen?
3, 2, 1, fire.
The particles explode. They explode from regions of high to low concentration. And as you can see in this video, self-propulsion dramatically enhances the diffusivity of an object. Let's see that more concretely in this slide right here. On the right-hand side, we have the same active system that you just saw. On the left-hand side, we have particles that do not self-propel. They move only due to translational Brownian motion. In both systems, we have regions of high concentration and low concentration far away. And I'm going to let go of the particles at the exact same time, at the exact same frame rate. And I wanted you to compare the relative speeds at which the objects spread out. Ready? Go. Whereas on the right-hand side, this active system is homogeneous. On the left-hand side, we still have regions of dense clusters and dilute regions far away. So the particles are diffusing much more slowly down their concentration gradients. The diffusivity on the left-hand side follows what is called the Stokes-Einstein-Sutherland diffusivity, d0, which is equal to the thermal energy scale, the Boltzmann's constant times the temperature, divided by the drag factor zeta, which in this case is 6 pi eta, the viscosity of the solvent, times A, the size of the particle. On the right-hand side here, we have these Janus particles that are also microns in size, so they too have a d0, the same d0 as the left-hand side, plus an additional contribution due to self-propulsion. And we know what that term is. It's just the drunken trajectories of these active particles. And when you plug in some numbers, you find that this self-propulsive contribution is 1,000 times larger than the passive contribution. So we can safely ignore d0 for an active matter system. And this is the reason why this poor drunken man can get home relatively quickly. Even if he had no sense of direction, he was just bolting off into random directions, his cloud of trajectories spread out significantly faster because he is able to self-propel. The same is true for a bacterium in its quest to find food. So at this stage, we know a lot about how objects spread out and diffuse. Turns out that there's a direct relationship with how things spread out and the unique mechanical pressure that they exert. In fact, the mechanical pressure pi is equal to n zeta d, where n is the number density or concentration of particles, zeta is the drag factor, and d is the diffusivity. This relationship applies for any source of random motion. For example, if we have a particle that does not self-propel, that moves only due to Brownian motion, its diffusivity is given here. We can substitute that diffusivity into there, and we find that the mechanical pressure exerted by a passive particle is given by its concentration times its thermal energy scale. We can rewrite the number density as the number of particles divided by the volume. When you do that, we find PV equals nKT. That is just the ideal gas law that you find in your high school chemistry classes. This is called the osmotic pressure. Now, let's do the exact same thing for an active body, which diffuses in this way. Substituting this diffusivity into there, we find that the mechanical pressure exerted by an active body is given by n zeta u squared tau r over 6. And this is what we coined the swim pressure. And at this stage, you might be wondering, what does it mean for an active body to exert a pressure? I mean, physically, what does this expression mean? To do that, let's go back to Disneyland. I often tell my boss that every time I go to Disneyland, I'm actually doing rigorous academic research. And you actually find that because this ride has walls along the outside. And you'd say, of course there are walls along the outside, because otherwise, crazy people like me would never get off the ride, would be able to escape the arena and to wander off into other parts of the theme park. So the walls are there to confine and prevent me from getting away from the arena. Maybe the same thing is true for an active body contained inside a container. Due to its drunken trajectory, it's going to collide into the bounding surfaces of the box, and you would need to exert a force or a pressure to contain or confine that body to stay inside. And that confinement pressure is precisely the origin of the swim pressure. And it is literally equal to the force on these walls divided by the area. We believe that the swim pressure is an important discovery that we made, which has applications in many different areas, from experiments to theoretical work. Today, I will present 3 particular examples and uses of the swim pressure. How the swim pressure can be used to compute the mechanical forces inside a biological cell, how it can be used to develop micromechanical devices, and lastly, how it can be used to predict the collective motion in active systems. So let's get started with this left-hand side. On this video on the left, we see malaria parasites that have infected a red blood cell. They multiply to a point where it causes the red blood cell to burst open and rupture. As I said earlier, the physical mechanism that mediates the release of intracellular components from an infected cell are poorly understood. These malaria parasites do not self-propel, so they do not exert the swim pressure. However, I still believe that it is a buildup of internal pressure inside the cell relative to the outside that causes it to burst open. In this case, that internal pressure is dominated by interparticle collisions between the parasites, especially at high concentrations near close packing, where those interparticle collisional forces and pressures diverge to an extremely high value. On the right-hand side, we have Listeria bacteria that do self-propel. And you can see that because these black rod-like objects are swimming around inside an infected eukaryotic cell. And we can see the outline of that cell, the cell membrane, right here. And if we focus on the cell membrane around the perimeter, for example, right around there, we see that the Listeria will collide into the cell membrane, locally deform it before being pushed back in. So in this case, the Listeria are exerting the swim pressure. And we now have a quantitative procedure to compute those forces and those pressures that the Listeria bacteria exert on the host cell. The main molecular ingredient of the cell membrane is called a phospholipid, which has a head group which likes to be on water and a tail group which doesn't. So when you put them in an aqueous environment, they form a 2-layered structure called a bilayer, which can then form a spherical shell with an empty, hollow interior. These are called vesicles. Vesicles are formed throughout our bodies and within our cells, and they are used as containers that transport important nutrients and waste products within our cells. And they are special containers in that they are semi-permeable. They allow the passage of certain species, such as water and oxygen, but they do not allow the passage of other species, such as large molecules like glucose and any charged species like salts. So you can think of them as a material that is somewhat analogous to Swiss cheese. They allow the passage of certain species like water, but they don't allow the passage of mice. There are synthetic ways to produce these vesicles. One of them is called electroformation. And Hunjin Lee and Rob Phillips' group taught me how to do this. You take a glass slide that is coated with a conductive material. Then you take a thin layer of phospholipids and coat it on top. In my experiments, I mixed in a little bit of fluorescently labeled phospholipids so that I can see them under fluorescence microscopy. On top of this, you take a droplet of solution and place a droplet. You take another glass slide that's conductive and form a sandwich. To this system, you hook up some electrodes, and you send in an alternating voltage, and inside this vesicle, you form vesicles. Inside this droplet, you form vesicles. And I'm going to take this balloon here and blow it up. Okay. Vesicles are three-dimensional and spherical in shape, much like this balloon. Suppose that I take this vesicle, take a cross-section right down the center. I take one half of it and turn it and expose the inside towards you. That's what you're seeing on the video right here. The bright ring you see on the outside corresponds to the edge of this vesicle. And inside, there's nothing, because there's nothing inside the vesicle. Remember that this vesicle is made out of a material that is analogous to Swiss cheese. So imagine that I add salt outside the vesicle. Salt cannot pass through the vesicle, but water can. Because there's an imbalance of osmotic pressure inside and outside, water will flow out of the vesicle, and what we get is a very floppy and flimsy vesicle, like the one you see here. Physically, this is manifested in the form of a reduced tension along the surface of the vesicle. So it is very easy to control the tension and the flimsiness of these vesicles. So next, my goal is to put active matter into this guy. And to the best of my knowledge, there is no one who has put active matter inside a synthetically created vesicle. And as a theorist, it took me a long time to figure it out. But ultimately, I came up with a method to encapsulate any micron-sized object inside of a vesicle. Here we see Janus particles inside of a vesicle without any hydrogen peroxide. So they do not self-propel, and they move around only due to Brownian motion. So you can see them jiggling around. Now we have this system with Janus particles on the inside. What I do next is to add hydrogen peroxide outside the vesicle. Just like water, peroxide can slowly diffuse through, and once they get inside, they react with the Janus particles, and what we get is that these particles become extremely active, and they self-propel. Both of these videos are taken at the exact same frame rate, so you're seeing an actual enhancement in the propulsive speed of these particles. So the system on your left exerts zero swim pressure. On the right exerts a non-zero, finite swim pressure. And you can see that by these particles swimming around, bumping into the walls, and turning back. So at this stage, I have a system to encapsulate any micron-sized object inside of a vesicle. And I wanted to see if I can make a model system of an infected cell, like the one you see on your left. So I took a species of grass bacillus and encapsulated it inside of a vesicle. And here's what I saw. The rod-like structures you see on the inside are the bacillus bacteria, and they are swimming around very actively. And you can see clear deformations taking place around the surface of the vesicle due to the swim pressure. In particular, we see the formation of these strings that pop out from the main vesicle, like right here. And then they ultimately get sucked back in. I took a snapshot of one of those instances. It's shown right here. So these three bacteria had so much propulsive speed and force that when they bumped into the cell membrane, they continued to push against it, and they've actually managed to pull out a thin tether or a membrane tube that extends out from the main vesicle. So these three bacteria are still a part of the main vesicle, and once they reorient and move off in a different direction, they work their way back inside. And these tethers can be 30 or 40 microns or even bigger in length. And if you look at an actual infected cell back here, we see that these listeria do the exact same thing. They bounce off into the walls, and they form these membrane tubes right around here. Even though the species of bacteria that I'm using are different, I've managed to qualitatively capture the features of an infected cell. The first time I made this measurement, all I can think of was gross and yuck. Just imagining that this is what may be happening to my poor cells when I get the stomach flu. And just like that, I became a germaphobe. Get your flu shots. This species of bacteria is very unique in that they significantly reduce their propulsive speed. They become very sluggish when they are exposed to poor growing conditions or starved for food. So I took bacteria that were starved for food into this into this vesicle, and you see that they're moving very sluggishly. They're not very happy because they're starved. And in this image, I've used both fluorescence microscopy, which allows us to see the edge of the vesicle, the fluorescently labeled phospholipids, in addition to bright field microscopy, which allows us to see the bacteria on the inside, which are not fluorescently labeled. When I take off the bright field, you can just see the edge of the vesicle. And if I didn't tell you anything, you might not even know that there are bacteria inside because there are no deformations taking place along the edge of the vesicle. Now, just as I encapsulated these bacteria inside, I fed it fresh food, fresh nutrients inside the vesicle with them, and the same concentration outside to osmotically balance the inside and outside. So these bacteria are just realizing that they have all this food around them. And if you were in a room full of food, you become very happy. And so when I wait a little bit of time, these bacteria become very happy. And you can see that they're very happy because they're moving around like crazy inside the vesicle. All of these videos are again played at the same frame rate. Now you can see a clear influence of the swim pressure. On the left-hand side, we have zero or very little swim pressure. On the right-hand side, we have high swim pressure. And you can see those deformations taking place. We can compute the magnitude of the swim pressure in this case, which is theoretically about 0.1 pascals. Compare that with the atmospheric pressure that we live in, which is 10 to the 5 pascals. So the swim pressure is an extremely small quantity, but it makes an appreciable influence inside of our cells. The one thing I wanted to talk about on this slide is that the swim pressure is equivalent in concept to the osmotic pressure. Suppose I take this balloon, this vesicle, and put salt on the inside. Salt cannot pass out of the vesicle, but water can pass in. Due to an imbalance in the osmotic pressure inside and outside, water will flow in, causing this vesicle to expand in volume. In this active matter case, the bacteria cannot pass through the vesicle, but water can. Because there's an imbalance of swim pressure inside and outside, water will flow in, causing the vesicle to expand in volume. Identical in principle. I took the same system of bacteria and vesicle and took a time lapse over time. The bacteria on the inside continue to multiply and grow, and the swim pressure inside is increasing. And this is what I saw eventually.
3, 2, 1, fire.
The bacteria explode out of the cell and go on to infect your other cells in your body. The swim pressure just before explosion was just above 0.1 pascals. Although the swim pressure is likely not the only contribution that causes infected cells to burst open, I do think it plays a significant role. And currently, I am conducting further experiments to assess just how big of a role it plays. Now, let's talk about the exact same experiments, but in a different application. Think about how those experiments can be used to develop mechanical devices. To do that, let's change our system of bacteria. Magnetotactic bacteria are unique in that they have magnetic crystals inside of their body that allow them to orient with an external magnetic field. Here I have a uniform magnetic field pointed in the shown direction by the arrow, and all the bacteria are swimming towards it. And when I change the direction of the field, it instantaneously changes directions and starts swimming in that direction. The strength of the magnetic field I'm using here are easily realizable by any household magnet. So I took these bacteria and encapsulated it inside of a vesicle. Initially, the field is turned on to the left, and the bacteria you see on the inside here are these spiral-like objects that are all swimming towards the field, and they're actually bunched up all against the left-hand leading edge of the vesicle, causing the entire vesicle to translate in that direction. And soon I'm going to turn off the external field, and you're going to notice a difference in the behavior inside, right there. So now we see that the bacteria are swimming randomly in every direction and no longer bunched up against the leading edge. We can track the center position of that vesicle with time, and in a direction parallel to the external field looks like this. The position increases towards the direction of the field with time when the field is turned on, and when I turn the field off, it suddenly stops at that position and doesn't move. This is in a direction parallel to the external field. In a direction perpendicular to it, it simply fluctuates about its initial value. The slope of this curve in the parallel direction gives an average speed of the translating vesicle, which in this case happens to be around 0.2 microns per second. So I can steer a vesicle at will. I can also deform it as well. Here we have magnetotactic bacteria encapsulated inside a vesicle that is more flimsy and floppy, so its tension is lower. Initially, the field is turned off, so that the bacteria are swimming randomly in every direction, and so the shape of the vesicle fluctuates, but stays mainly spherical. And soon I'm going to turn on the external field suddenly, and you're going to notice a dramatic change in the shape of this vesicle. So I wanted you to pay attention to the shape change. Right there. So now the field is turned on, and the shape of it changed from something that was spherical to something that is more ellipsoidal. Inside this vesicle, we have bacteria that swim towards the North Pole, so swim towards the left-hand side, and mixed in there is also a species of bacteria that swim towards the South Pole, so swim towards your right. So imagine that initially, when the field is off, they're swimming randomly in every direction, and then suddenly I turn on the field, and they start swimming in opposite direction, which causes the entire vesicle to deform and take the shape of a football. There is a quantity called the eccentricity, which is a geometrical property that measures how spherical an object is. When the eccentricity is 0, then the cross-section is a perfect sphere. When it is larger than 0, less than 1, then it is an ellipse. So initially, when the field is off, like I said, the vesicle shape fluctuates. And you can see those fluctuations in the eccentricity. It fluctuates in value. But just as I turn on the external field, we see a sudden shape right there, a sudden jump in eccentricity from around 0.4 to 0.8, and it stays at that value and doesn't fluctuate for the duration of the field turned on. So I can steer a vesicle, and I can deform it as well. Now I have a soft material where I can load the inside with active matter. Due to the swim pressure, it may deform and expand. If I have orientable microswimmers inside, that I can control it to make it all go in the same direction, I can make the entire vesicle translate in that direction. If I control the mechanical properties of that material, namely the tension, then I can make it deform as well. Although this concept is still far from material where it can deliver a particular drug to a particular place within the cell, I believe that having a material where I can make it expand, shrink, bend, contract, deform, and steer it at will is a good first step towards such a biomedical application. Aside from that biomedical application, I believe that this kind of material can be used in general for any micro or nanomechanical device. Now, let's switch gears a little bit and talk about something entirely different. To be honest, up until now, I've just shown you a bunch of pretty videos that were fun to watch. But from this point onward, I'd like you to do a little bit of mental gymnastics because we're going to talk about how the forces inside a biological cell, how the development of mechanical devices can predict the collective behavior seen in active systems. So let's get started. From birds to fish to microscopic Janus particles, active systems have a tendency to swarm together and move collectively as a unit. Physicists have been both intrigued and confounded by this behavior because we simply don't know why they do so. Until the swim pressure. We're going to use the swim pressure together today to explain this behavior. Here are some computer simulations that I conducted. On the left-hand side, we see a bunch of blue dots on your screen. Those represent microscopic particles. Over here, they do not self-propel, and they move only due to Brownian motion. And the system remains largely homogeneous. Whereas on the right-hand side, these particles do self-propel, and we see a significant difference in their behavior. The particles are clumping together and forming large clusters. This is an extremely strange process, to have a system that begins initially homogeneous transition to an extremely inhomogeneous system. And this system and this process reminds us of an equilibrium gas-liquid coexistence process. For example, the water vapor in this room condensing together to form a liquid droplet. But unlike that equilibrium system, where the molecules attract each other, in my computer simulations, there are no such attractions. So the particles have purely excluded volume, or hard sphere potentials, which is no attraction at all. But yet, the particles are attracting. They're clumping together and forming large clusters. All throughout today, I've told you that a drunken trajectory in diffusion tends to spread things out. But now it's doing the opposite. The objects are coming together. How could that be? To help us is the swim pressure, which I told you for an infinitely dilute suspension is given by this expression. And that is the pressure that this active body exerts on the bounding surfaces of the box. What happens to this value at larger concentrations? At larger concentrations, as you saw in the simulation, the particles form large clusters. Let's focus on that 5-particle cluster for the moment. Suppose, for the sake of argument, that the velocities of those 5 particles cancel out exactly, such that those 5 particles as a unit has a net speed of 0. They just sit there. They don't move around. How much pressure do those 5 particles exert on the bounding surfaces of the box? 0, because they just sit there. They're not spending any time colliding into the outer box. So we expect the swim pressure to decrease with concentration when clusters begin to form. Here are some Brownian dynamic simulation that we conducted of the swim pressure, or the confinement pressure, as a function of concentration. Initially, for small concentrations, the swim pressure increases because the more swimmers I add into the box, the more collisions with the outer boxes, the higher the swim pressure. But beyond a certain point, when clusters begin to form, the swim pressure decreases with concentration for the reason that I discussed in the previous slide. There is one parameter that I haven't introduced to you yet, which is the reorientation Peclet number, which is a ratio of the swimmer size A divided by the run length of that swimmer. So for a very large Peclet number, the swimmer takes short steps and reorients quickly. So they look something like this. They take a step, reorient, step, reorient, step, reorient. This looks just like a Brownian particle. And Brownian particles don't condense together to form clusters. So the swim pressure increases monotonically with the concentration until very high concentrations near close packing, where the swimmers collide into each other before being allowed to take a step. So the swim pressure all decreased to 0 near close packing. There is an additional contribution to the pressure due to interparticle collisions between the particles. For a hard sphere or excluded volume potentials, those are simply collisions. When you have higher concentrations, particles collide into each other, and due to their collisions, they exert a pressure on the system. And the more particles you have, the higher concentration, the more collisions going on. So we expect the collisional pressure, pi p, to increase with the concentration of particles. And that's what we see in our Brownian dynamic simulation. Pi p, collisional pressure, as a function of concentration, increases for all values of the Peclet number. And at close packing, the interparticle collisional pressure diverges to infinity. So now we have two contributions to the pressure. The swim pressure, or the confinement pressure, which decreases with concentration after clusters begin to form, and an interparticle collisional pressure, which increases with concentration. We're going to add the two together and call that the active pressure, as the total pressure that the particle exerts on the system. What happens if you add a decreasing function with an increasing function? We may get something that looks like that, a non-monotonic pressure profile. In classical thermodynamics, such a profile indicates a gas-liquid equilibrium process. So let's take a look. Here is the active pressure, the sum of the swim pressure plus the collisional pressure, as a function of concentration. For large values of the Peclet number, say for this black curve, again, that system behaves like a Brownian particle system. They don't condense together, and hence we get a monotonically increasing active pressure with concentration. But as we increase the run length, decrease the Peclet number, clusters begin to form. And now if you take a look at this red curve for a very small Peclet number, it initially increases, flattens out, and then increases again. That looks just like that. And in classical thermodynamics, this is called a van der Waals loop. And the flat region of this pressure profile indicates the region where the gas and the liquid coexist together. In this curve here for the red, it would be something around 0.3 to 0.6. So between a concentration of 0 to 0.3, the system is homogeneous. No large condensations form. Between 0.3 and 0.6, large clusters begin to form, like that. And beyond 0.6, we have yet again another single crystal phase. If you open any thermodynamics textbook, you are sure to find a profile that looks like that, a pressure-volume phase diagram. Here I'm plotting the volume fraction, which is the inverse of the molar volume. So I'm going to flip this figure around, and now the two graphs look identical. And at this point, you might be wondering, what about this ride? Why doesn't the vehicles cluster together? Well, the answer is right in front of us. I went to Disneyland for work, and I measured the concentration, which happened to be around 0.1. Let's return to this initial graph here. 0.1 is well within the single phase region, so that's why they don't cluster together. And I would expect if you add in more vehicles, you would see a condensation happening. Although, I don't know how fun the ride would be if it's so crowded. The most significant aspect of this development is that we now have an equation of state of an active matter system. In classical thermodynamics, having an equation of state is significant because it allows us to compute almost every property about that system. Here, in this active matter case, the swim pressure plays the essential role within this equation of state. So the swim pressure allows us to predict the collective behavior seen in active systems. Today, I hope I convinced all of you that all active matter systems trace out a drunken trajectory. And by virtue of their drunken trajectory, we all exert a unique micromechanical swim pressure. I focused on three particular examples today, how the swim pressure can be used in biology, chemistry, and in physics. But we believe this is just a start, and that the swim pressure is a brand new perspective that will allow us to analyze many, many more systems to come. The next time you find yourself tracing out a drunken trajectory, right before the moment you collapse on the side of the street, I hope you remember that all you are doing is exerting the swim pressure. I have a lot of people I need to thank for this presentation. first of all, Professor Everhart and the entire Everhart Lecture Series Committee for allowing me to speak today and improve my presentation. Also, I wanted to thank my entire group, John Brady's group, especially my advisor, John Brady, who has been flexible enough, maybe I should say crazy enough, to allow a theorist to learn how to do experiments. There's an African proverb that goes, "It takes an entire village to raise a child. It takes an entire village to train a theorist how to do experiments." And my villages consist of Ralph Didier, Jan Vermont at ETH, and Mikhail Shapiro and Rob Phillips's groups, and many other groups that I couldn't mention here that all have given me help. And they have literally given me the keys to all of their equipment, which is probably a dangerous thing to do. But thank you so much. And lastly, I wanted to thank all of you for coming here today. Thank you so much. 本当にありがとうございました。